Today we're going to talk about trig ratios of any angle. Let theta be an angle in standard position, and let P, the point, the xy, be any point on the terminal side of theta. Let r equal the distance from the origin, such as we have set up in this picture to the right here. So if we want to figure out what r is equal to, of course we can use our Pythagorean theorem, which states that x squared plus y squared equals the hypotenuse squared. So the hypotenuse is across from the right angle, which is r. So if we want to solve for r, it's the square root of x squared plus y squared, because to get rid of the power of 2, take the square root. And normally we do plus or minus when we take away the power, but since we're talking about a distance, we don't use the negative. So the sine of theta in this case, we know, of course, so toa. So the sine we know is opposite over hypotenuse. So in this case would be y over r. And the cosine is adjacent over the hypotenuse, so x over r. And tangent is opposite over adjacent. So if our r value is 1, so when r equals 1, think about your unit circle, then that would mean sine of the angle theta is equal to y. The cosine of the angle theta equals x, and we can write tangent of theta is equal to sine theta over cosine theta. Note that the point P can be any point on the terminal side of the angle except the origin, since different choices for P generate similar triangles. Thus, the values of a trigonometric ratio depend only on the angle. So when you're making a triangle, you always want to make the triangle with the x-axis. So if you always want the shortest angular distance, so if you're on the right side of the circle, you use the positive x-axis. If you were on quadrants 2 and quadrant 3, you would use the negative x-axis. So let 6, 8, and 3, 4 be a point on the terminal side of theta. Find the sine, cosine, and tangent of theta. So for this, if we look at first the 3, 4 point, so to get to that point, we went over 3 for x and up 4 for y. So we can solve to find r. So first we're going to do the point 3, 4. So r is equal to the square root of x squared plus y squared, which is, 4 squared. And so when we do that, that gives us 9 plus 64, which when we take the square root of that, which is 25, we get 5. So this is, of course, a 3, 4, 5 triangle. So I'm going to erase that r and put 5 there. So if we want the sine of theta, of course, is equal to opposite of the hypotenuse, so 4/5. The cosine of theta would be equal to adjacent over hypotenuse. And the tangent of theta we know is sine over cosine, or we know in this case if we have the triangle, opposite over adjacent, so 4/3. So that is for the point, again, 3, 4. If I do the point 6, 8, so now the x value to get over here would be 6 and up 8. So now we have to solve for r. So r is equal to the square root of 6 squared plus 8 squared, which is equal to the square root of 100, which gives us 10. So that tells us that r is 10 for this triangle. And so for this, then with our triangle, and I'm going to just redraw it over here to make it a little easier. So we have 6, 8, 10. So the sine of the angle theta is equal to opposite over the hypotenuse. So 8/10 reduces into 4/5. The cosine of theta is adjacent over hypotenuse, so 6/10, which reduces into 3/5. And the tangent of theta is equal to 8/6. because opposite over adjacent, which reduces into 4/3. So notice that, again, like we said, so in this case, we have the 0.34 and the 0.68, which of course have different radiuses, but the trig ratio ends up being the same, which is why we like using our unit circle, because it's, like we said before, the values of a trigonometric ratio depend only on the angle. So they have the same angle, different radius, but they still give you the same trig ratio because it reduces into the same thing. So just to show you, if we wanted to find theta, which was not one of our questions, remember that to find theta, we could do our inverses. So theta would be equal to, if we did sine, the sine inverse of the trig ratio. And we could do theta equals the cosine inverse of the cosine trig ratio, which was 3/5. And theta equals the tangent inverse of 4/3. So if you wanted to do this in your calculator to find the actual, what the angle is equal to, you could use any one of these inverses, the sine, cosine, or tangent. Make sure your calculator is in degree mode, which mine is. And then at the home screen, you can do second sine, which gives you sine inverse. If I do 4/5, I get 53.13. So even if I did instead cosine of 3/5, because that was the trig ratio, notice that I get the same answer, or I could have done the tangent of 4/3, and I would still get 53.13, because again, they're using the same angle, so I should get the same answer. So theta is equal to 53.13 degrees. Again, that wasn't one of the questions, but I'm just showing you that you can find it if you had to. So for the next example, it says, find the sine, cosine, tangent of angle theta whose terminal side passes through the point -3, -2. So that tells us -3, -2 is in quadrant 3. So we're going an x value of -3 and a y value of -2. So our triangle's made with the x-axis on the negative side, and that would be our angle theta. So we just need to figure out what r is, our hypotenuse. So r is equal to the square root of x squared, so -3 squared plus y squared, -2 squared, which gives us the square root of 5. So now I just want to find, or not the square root of 5, the square, what am I doing? The square root of 13, think about the next problem. So I need to find the sine of the angle. So opposite over hypotenuse, opposite is -2, hypotenuse is root 13. But remember, we don't like to have radicals in our denominator, so I'm going to rationalize this. So multiply this by root 13 over root 13, and that gives us -2 root 13 over 13 after we rationalize it. So that's the sine. The cosine of the angle would be equal to adjacent over the hypotenuse. Again, we need to rationalize that by multiplying by the square root of 13 over the square root of 13. So that gives us -3 root 13 over 13 for the cosine. And the tangent of the angle theta would be equal to opposite over adjacent. So that just gives us 2/3. So those are the trig ratio for sine, cosine, and tangent of the angle theta whose terminal side passes through the point -3, -2. So why don't you go ahead and do the next one on your own, and when you're done, you can pause to check your work. So we're doing the same thing, except for we're using the point 2, -1, which we know would be in quadrant 4. So we're going over 2 and down 1. So that would be our triangle. And we need to find r. So r is equal to the square root of 2 squared plus -1 squared, which this one is the square root of 5. So then for this, if we want to find the sine of the angle, opposite over hypotenuse, -1 over the square root of 5, and then we need to rationalize root 5 over the square root of 5. So this gives us negative root 5 over 5 for this sine. Cosine of the angle would be equal to adjacent over hypotenuse. And then when we rationalize, multiply by root 5 over the square root of 5. And we end up with 2 root 5 over 5. And then the tangent of the angle is opposite over adjacent, so negative 1/2. And those would be all the values. Now we're going to look at some tips and tricks for helping you recall the unit circle faster. So we know, I'm going to start off with the degrees in the inside. So we know we start off with 0 degrees here. So the first one we know for our special right triangle that we use is the 30 degrees. So let's go ahead and start by just counting with the 30 degrees. If I count another 30 degrees, that would put me at 60 degrees, which we know is here. Plus another 30 is 90 degrees. Plus another 30 is 120 degrees. Plus another 30 is 150 degrees. Then another 30 would be 180 degrees. 210 degrees. This would be 240 degrees. 270 degrees, 300 degrees, 330 degrees, and all the way around, of course, we know is 360 degrees. So you could count by 30 degrees for those values. We know, remember, the middle one was 45 degrees, so you could count 45. 45 plus 45 is 90. 90 plus 45 is 135 degrees. Plus another gives us 180. Plus another 45 would be 225 degrees. Another would be 270, another would be 315 degrees, and then back to where we started. So that would be counting by 45 degrees on my circle, or you can notice that, each one between is 15 degrees, so you could count that too, whatever helps you. And for our radian measures, we talked a little bit about this in the last video, but the first angle, remember, we can count by, if we look at this, we can count by pi over 6. So if you don't remember, 30 degrees times pi over 180 ends up being, if you cancel out the zeros, you get 3 pi over 18, which reduces into, of course, pi over 6. So we're just going to count by pi over 6. So 1 pi over 6, this one right here would be 2 pi over 6, but we want to reduce that. So when you reduce it, you get pi over 3. Then we have 3 pi over 6, which reduces into pi over 2. The next one would be 4 pi over 6, which reduces into 2 pi over 3. And then we have 5 pi over 6, which doesn't reduce. 6 pi over 6, of course, is just pi. Then we have 7 pi over 6. This next one would be 8 pi over 6, which reduces into 4 pi over 3. And then we have 10 pi over 6, which reduces into 3 pi over 2. And next one would be 9 pi over 6. 9 pi over 6. And then this one would be 10 pi over 6. Sorry, it's getting late here. So 10 pi over 6 reduces into 5 pi over 3. And then 11 pi over 6. And then, of course, 12 pi over 6 gives us 2 pi. So we start off with 0 radians and we end with 2 pi, which would be all the way around. So that gives me counting by pi over 6. So again, 1 pi over 6, 2 pi over 6, 3 pi over 6, 4, 5, 6, all the way around, and you just reduce those values. So we don't have to just count by pi over 6. We can also count by the 45 degrees around our circle to get those values. So the next one I'm going to do. So if I do the 45 degrees, that's pi over 4. So then if we count 1 pi over 4, 2 pi over 4 reduces into pi over 2. And then we get 3 pi over 4, 4 pi over 4 reduces into pi, 5 pi over 4, 6 pi over 4 reduces in 3 pi over 2, and then 7 pi over 4. And then, of course, 8 pi over 4 would be 2 pi. So then, again, that's just another way of counting around your circle to get the pi's over 4. So now we have all the radian measures around our circle. Something else that you can notice with your radian measures. So notice that these values here are going all by over 6. Oops, there. So those values all go over by 6 because that is with the 30 degrees. So if you think about your reference triangle that we drew before here, these are all using that same reference triangle of 30 degrees. And so it makes sense that they're over 6 for the denominator. You can say the same thing about the 45 degrees with the over 4. So notice this is pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. And then with the 60 degrees, we use over 3. So notice so this is quadrant 1. So notice in quadrant 2 that the denominator is 1 more than the numerator. So 2 over 3, 3 over 4, 5 over 6. In quadrant 3, notice that the numerator is 1 more than the denominator. So 7 over 6, 5 over 4, and 4 over 3. And then in this quadrant 4, somebody once said, well, the denominator is times 2 plus or minus 1. So 3 times 2 is 6, minus 1 is 5. 4 times 2 is 8, minus 1 is 7. 6 times 2 is 12, minus 1 is 11. Whatever helps you to memorize those values, that's fine. You don't have to use that. It's just what somebody said one year, stuck with me. So then we have our coordinate order pairs on our circle. So we know that this point on my circle, the radius of the circle we know is 1, so you're going over 1 up 0. And remember we said that the circle coordinate order pairs are cosine of the angle comma sine of the angle. So up here we know this is over 0 up 1, and then at pi or 180 we have negative 1, 0, and then down here at 3 pi over 2 or 270 we have 0 and negative 1. So the signs change, of course, depending on what quadrant you are in. So then for the first one, using the 30 degrees, we talked about this for our unit circle values. We said this was root 3 over 2 and 1/2. And remember, we said that all of the 30 degree reference angle triangles and angles are going to be the same. So that reflects over to the 5 pi over 6, which again in this quadrant would be negative x, so negative root 3 over 2 and 1/2. And that's 7 pi over 6 or 210 degrees. We get negative root 3 over 2, negative 1/2. And then in the fourth quadrant, the point would be root 3 over 2 and negative 1/2. So again, just the signs changed. And the middle one, we know, of course, is root 2 over 2, root 2 over 2, because we talked about, again, how to get these using our special triangle. So this would be negative root 2 over 2 and root 2 over 2. In the third quadrant, we would get negative root 2 over 2 and negative root 2 over 2. And in the fourth quadrant, root 2 over 2 and negative root 2 over 2. And then for the last point, which is using the 60 degrees as our reference angle, we have 1/2 and root 3 over 2. So the points flip from the 30 degrees because you're just changing the way the triangle is set up from what we learned. So this would be negative 1/2 root 3 over 2. Down here would be negative 1/2 negative root 3 over 2. And of course, this last point would be positive 1/2 and negative root 3 over 2. So that gives me all the coordinates around my circle. So again, you just notice that the signs are changing. So if you know the first quadrant, you really know all the rest of the quadrants. And I feel like 45 degrees is the easiest because it's always root 2 over 2. And we'll talk about another trick that I'll show you that you can do, or show you a video you can watch for a hand trick that actually helps with this as well. So something we haven't talked about, so we know that the coordinates on the our coordinates around our circles are cosine theta comma sine theta. So we already talked about if I wanted to find the cosine of 60 degrees, well, that would be the x coordinate on my circle, which would be equal to 1/2. If I wanted to find the sine of, let's say, 3 pi over 4, that's in quadrant 2, and the sine is the y coordinate, which would be root 2 over 2. So we can also do this with tangent, because we talked about up here, remember that tangent is sine over cosine. So we know that's tangent of the angle equals the sine over the cosine which again is y over x. So we can use that to help us find the tangent values on our circle. So if I wanted to find the tangent of 30 degrees, I would do the sine of 30 degrees divided by the cosine of 30 degrees. So that would give me sine of 30 degrees is 1/2. Cosine is equal to root 3 over 2. So if you have a fraction divided by a fraction, you keep change flip. So keep the 1/2, change multiplication, and flip. And notice the 2's would cancel out. So you multiply straight across, 1 over root 3. Of course, we want to rationalize our denominator there, so multiply by root 3 over root 3, and we get root 3 over 3. So that would be the tangent of 30 degrees. I'm going to write that on the outside. So the tangent of 30 degrees is root 3 over 3. If I did the tangent of 150 degrees, so 150, we're using 5 pi over 6. So the sine of 150 degrees over the cosine of 150 degrees. So that gives us 1/2 over negative root 3 over 2. So notice that it's going to give us the same answer, just the sign change. So we have keep, change, and flipped. So those cancel out to give me negative 1 over root 3. And then when you rationalize, we get negative root 3 over 3. So again, notice it gave us the same answer, it's just that now it's negative in this quadrant. So this is negative root 3 over 3. And actually I'm going to use another color. So negative root 3 over 3. If I did the tangent of 4 pi over 3, so now that's in quadrant 3. So the tangent of 4 pi over 3 would be the sine of 4 pi over 3 divided by the cosine of 4 pi over 3. So the sine value is negative root 3 over 2, and the cosine is negative 1/2. So keep, change, flip. So keep negative root 3 over 2, change, and flip this to 2 over 1. And so the 2's cancel out. So we end up with negative times negative is positive. So root 3 over 1, which is just root 3. So this value ends up being root 3. And you can do that for any values for tangent. So notice that if I were to do the tangent of 45 degrees, sine over cosine would be root 2 over 2 divided by root 2 over 2, which is the same thing, which gives you 1. And if I did pi over 3, I would get root 3. Here, sine over cosine would be 0 over 1, which is 0. And up here, we would have, at 90 degrees, 1 over 0, which is undefined. So just like our coordinates for sine and cosine just change, the sign changes depending on the quadrant, the same thing for tangent. So here, if sine and cosine are opposite signs, so sine is negative and sine is positive and cosine is negative here, you would get negative 1, and this one would be negative root 3. Over here, you still get 0 at pi. At 7 pi over 6, you would get, again, negative divided by negative means tangent would be positive here, so root 3 over 3, 1, and root 3 we already did. This is undefined again, because sine over cosine would be negative 1 over 0. And then here, notice that your cosine's positive and sine's negative, so again, that means your tangent would be negative, because again, it's sine over cosine. So negative root 3, this would be negative 1, and negative root 3 over 3. So again, just like if you know the first quadrant for your sine and cosine values, you basically know the first quadrant for tangent, which in pre-calculus, we also have the students memorize those so that they can recall them faster. So I would probably just practice this using a blank circle, you know, and seeing if you can write down the values, because if you memorize it now, it's really going to help you for later. So let's go ahead and look at using our unit circle and graphing our sine using radians. So we have our degrees, radians, and so when we're graphing these, we're going to use our radian values, and we have the trig values for the sine, the exact value, and the decimal approximation. We're just going to use the decimal approximation. So the sine of 0 degrees we know is 0, and you can even look at your unit circle for that. The sine of pi over 6. So again, if we go back to our circle, here is pi over 6. Sine's the y-coordinate, so 1/2. So that's why the next one here, you'll see at 30 degrees, the decimal approximation is 1/2. So pi over 6, 1/2. At pi over 4, we get root 2 over 2, which is 0.7 about. And pi over 3, we get root 3 over 2. And at pi over 2, we're at 1. Again, I'm just using the decimal approximation. At the next value adds 2 pi over 3. Notice now we're back at 0.8. And then root 2 over 2, so 0.7 at 3 pi over 4. 5 pi over 6 would be 0.5. At pi, we're at 0. 7 pi over 6 gives us negative 0.5. 5 pi over 4 would be negative 0.7, negative 0.8. And at 3 pi over 2, we're at negative 1 for the sine. So the sine of 5 pi over 3 would be about negative 0.8 because it's negative root 3 over 2. The sine of 7 pi over 4 is negative root 2 over 2. And the sine of 11 pi over 6 is negative 1/2. And the sine of 2 pi, which is the same as the sine of 0, is 0. So that gives us our first wave, which is one time around our circle. So from here to here is one time around our circle, one wave, or we call that the period of the function. And notice this is the middle where the graph is oscillating back and forth between. So if it's the middle, that's why we call this the midline. Just like when we had our Ferris wheel, the midline was the center of the wheel. So kind of the same idea. So it says find the following, the maximum. So if we look at our graph, you can see the maximum's at 1, the minimum's at -1. Your domain, your graph, you can go infinite many times around your circle. So the domain would be all real numbers, -infinity to infinity. And the range, of course, is from -1 to 1 for the highest and the lowest. So the midline, there is a formula to find. So the midline is the distance between the maximum and minimum value. So this is how we can find it. So the maximum plus the minimum divided by 2. So in this case, you have the maximum, which is 1 plus -1 divided by 2, which gives us 0 over 2, which is why the midline is at y equals 0. The length of one complete repetition of the cycle is called the period of the graph. This is the horizontal distance before the graph repeats. And so since the period is a distance, it is always positive. Important to keep in mind. And so what's one wavelength, or one time around our graph? We know it takes 2 pi radians. And to sketch the basic graph, it helps to note the 5 key points in one period. The key points are the maximum, minimums, and the intercepts of the graph, or where the graph crosses the midline. So to get the key points, you divide the period of the function into 4 equal parts. So it's the period divided by 4, which in this case would be 2 pi over 4, which gives us pi over 2. So these give us the key points. So the key points, again, are the place where it crosses the x-axis or the midline, because you might have transformations. The maximum points, here's the other place where it crosses, and of course the minimum point. So notice that there are 5 key points in one cycle. So if we think about the key points, notice that for this sine graph, it's 0, 0. Then we had pi over 2, 1, pi, comma, 0, 3 pi over 2, -1, and 2 pi, comma, 0. So those give us our key points. So again, notice there are 5 key points in one period. So again, the key points, if you think about the circle, so here, 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 and here. So where the graph crosses the midline and the maximum and the minimum of our graph. So we started off at 0 for sine, and then it was 1, 0, negative 1, 0. So back to the start. So that's why we have the 5 key points. But notice they're equidistant around. So we get that by dividing the period into 4 equal parts. The distance from the midline to the maximum minimum is called the amplitude of the graph. So if I look at from here to here, or from here to here, that is called, again, the amplitude. And same thing here. So to find the amplitude, you can take the maximum minus minimum divided by 2. So in this case, 1 minus negative 1 divided by 2 would be 2 over 2, which gives us amplitude of 1. So the amplitude for this graph is 1, which you can even see on your graph. So that is one wave of our sine graph. And of course, we could keep repeating those values to get another wave, but we're just going to leave it like that because we're going to talk about sine and cosine again later. So I want you guys to do this problem on your own. So this is now using cosine values on your circle, and then you're going to plot the points and then find the domain and range, and then answer these following things in the table right here: the maximum, minimum, amplitude, midline, period, and the key points. And that is it for this session.